There are three major types of material that exist in our universe. There are solids, there are liquids, and there are gases. We are going to talk about gases in this chapter. There are other types of matter. We just don't see them very often, so we're not really going to talk about them in this course at all. So this is just to sort of get you in the right frame of mind. You know that the air around you has molecules, atoms in it, but you can't really see it. So how do you know that that's true? I'm just looking for a practical explanation. And one of the more practical pieces of evidence that the air around us is actually made of stuff is that you can feel it. So maybe you can't see the air around you, but you can actually feel it. If someone, you can feel the breeze. So you know that there's stuff there, even though you can't necessarily see it. There's this thing at the beginning of the chapter on gases that your book talks about called the kinetic molecular theory of gases. I don't really care that you know this. I certainly don't care that you know the details of this, but I am going to go over it just again to put you in the right frame of mind. The theory says that gases consist of atoms and molecules that move around randomly. In other words, they're just sort of bouncing around. They don't have any particular place that they're trying to go, and they're moving around pretty fast. So just to give you an example, your average oxygen molecule in the room that you're in is moving at about 1,400 feet per second, which is pretty darn fast. More information on the kinetic molecular theory. There's a lot of empty spaces between gas molecules. That will basically explain why we can't see the air around us. And we can only feel it. So this is supposed to be a gas in a container, and these are supposed to be atoms or molecules, and they're bouncing around randomly, so they're just bouncing around with no particular direction that they're trying to go in, and these little zigzag lines are supposed to show you that they're moving around really fast, and then you can see that there is a lot of empty space in between them. This is a little bit mathy. It's saying that the average kinetic energy of gas molecules is proportional to the temperature of the gas molecules in units of Kelvin. And what this is basically saying, if you remember from much earlier in this course, kinetic energy is energy that materials have because they're moving. So what this bullet point here is saying is that the average energy, the average movement energy of gas molecules depends on what the temperature is, and it depends on the temperature in Kelvin. So if the temperature in Kelvin gets twice as big, if the Kelvin temperature gets twice as big, then the average energy of your gas molecules is going to go up by twice as much. If the temperature of your gas molecules goes down by 10 times in units of Kelvin, then the average kinetic energy of your gas molecules is also going to go down by 10 times. That's what this bullet point is saying here. You're going to see that Kelvin is going to be important in this chapter. Okay, so that's it for the kinetic molecular theory of gases. Like I said, I don't really want you to memorize that stuff or know anything in any more detail than what I just said. It's just to get you in the right frame of mind. Here's some stuff that I do want you to know. So when we talk about a gas, most of the time we are going to talk about a gas in a container. And to be perfectly honest with you, most of the time in these videos I'm going to be talking about a gas in a balloon, because that's the one that most of us are familiar with, and that's going to be my example a lot of the time. But when we are talking about a gas, there are a bunch of features of the gas that we can talk about. One of the features is called pressure, and that is basically the amount of force that these gas molecules exert when they slam into the sides of the container. So these things are moving around randomly really fast. They give little pushes to the edges of the container, and the amount of force that they give against the container is measured in something called units of pressure. And the abbreviation for pressure for us is going to be a capital letter P. Hopefully that is not too difficult to remember. Another feature of gases that we're going to be interested in is the temperature of the gas. So the temperature is going to be abbreviated with a capital letter T. We are also going to be interested in the volume of the gas. In other words, how much space does it take up in the container? That is going to be abbreviated with a capital letter V. And last but not least, we are going to be interested in the amount of gas in our container, in some pretend container, and that is going to be abbreviated with a lowercase letter n. You can think of this as standing for number of moles, and sometimes maybe number of molecules. Okay, so now we're going to go over these, at least the first two, bit by bit. Especially gas pressure. This is probably the one that people are the least familiar with. It turns out that there are many different units for measuring pressure of gases, and I'm going to show you some of them. My crappy joke is that I think a couple hundred years ago, everybody and their grandmother figured out how to measure gas pressure, and they named the units after themselves, and nobody wanted to back down, and so we are stuck with 10 million different units for describing gas pressure. So here are some of the 10 million. One unit for measuring gas pressure is called an atmosphere, and the abbreviation for atmosphere is ATM. There are many other units. There are units of pascals, atmospheres, millimeters of mercury, that is abbreviated mmHg because Hg is the symbol for mercury. Torr, that's named after a dead Italian chemist named Torricelli. There are pounds per square inch, inches of mercury. Everything here is just a different unit for measuring pressure of a gas. And there are pieces of conversion information to let you convert between these different units. So for example, 1 atmosphere of air pressure is the amount of air pressure that we feel from the outside air pushing against us when we are at sea level. And you and I are most likely very close to sea level, at least if you are living near where I am. In the eastern United States, I'm pretty close to sea level, and so the outside air pressure pushing against me is approximately 1 atmosphere. Turns out that 1 atmosphere is equal to 101,325 pascals of pressure. It's equal to 760 millimeters of mercury. It's also equal to 760 torr, and on and on and on. I do not expect you to know the conversion information between different units of pressure, but I may give you the conversion information for different units of pressure and expect you to be able to do the conversion. So like I said, there are many different units for measuring pressure. You should at least be able to recognize these units. You don't have to know the conversions, but you should know that a pascal is a unit for measuring pressure. You should know that torr is a unit for measuring pressure. Pounds per square inch, unit for measuring pressure. So here's my first demand. You should be able to convert between different units of pressure. Here's an example. 1 atmosphere of gas pressure is equal to 760 millimeters of mercury of gas pressure. And if that's true, so this is something that I would tell you on a quiz or a test, then the question I might ask is something like this. If the pressure in a balloon is 2.3 atmospheres, what is the pressure in units of millimeters of mercury? There are a billion different ways of solving this. The way that I would do it is this way. I would write this bit up here as a ratio. 760 millimeters of mercury is the same thing as 1 atmosphere of pressure. And then I would make an equal fraction off to the right, and I would say, but I don't have 1 atmosphere of pressure in my problem. I have 2.3 atmospheres of pressure, so I'm going to put 2.3 atm there, and I want to know how many millimeters of mercury that is, and I'm going to call that x. Then we can cross multiply and solve for x. So if we cross, we're going to do 1 times x is equal to 760 times 2.3. And, well, 1 times x is just x, so the answer is going to be 760 times 2.3. And that will be 1,748 millimeters of mercury. And again, I am not paying attention to the significant digit rounding rules. I just am trying to focus on doing the calculation correctly. So the answer to this question would be 2.3 atmospheres of gas pressure is the same thing as 1,748 millimeters of mercury of gas pressure. These are just different units for describing the same amount of pressure. There are a couple of big rules for dealing when we do calculations involving gases. And there are going to be 2 big rules. One of them is going to be obvious, the other one is not going to be so obvious. Here's the one that's not obvious, and here it is. Always, 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 when you need to use a temperature in one of your calculations involving gases, you have to always convert the temperature to units of Kelvin. And just to emphasize this, check this out. Wasn't that amazing? Isn't that amazing? That's Academy Award worthy special effect right there, that spinning always. Always convert to Kelvin. If I tell you that the temperature of a gas in a container is 20 degrees Celsius, don't use this in the calculation because you're going to get the answer wrong. You need to convert this to Kelvin. And if you remember, if you want to convert from Celsius to Kelvin, the temperature in Kelvin is whatever the temperature is in Celsius plus 273.15. I don't really care if you add the 0.15. It's probably never going to make a difference in the answer that you come up with, but there it is. There is a 0.15 there. So if I asked you, if I said the temperature of a gas in a container is 20 degrees Celsius and you needed to use the temperature as part of your calculation, you had better convert it to Kelvin, and then this would be the temperature in Kelvin, 293 Kelvin. The other rule is just a rule that is generally true when you're doing calculations. When you're using an equation, you have to make sure that the units match. What do I mean by that? If I tried to set up this relationship where the left side and the right side are equal to each other because there's an equal sign, this situation is bad. You can think about this for a minute. But the reason that it's bad is because I have liters on one side and I have milliliters on the other side. The units have to match in order for me to do the calculation correctly. So either I have to convert this to milliliters to get the equation to work correctly, or I have to convert this part here to liters. Either conversion will work and it'll give me the correct answer, but I have to pick one or the other. I can't leave the units as being milliliters on one side and liters on the other side. Okay, that is it for the introduction to gases. What's going to come up after this and all of the subsequent videos is just a parade of equations named mostly after dead people. So see you in the next video with the first dead guy. All right, bye-bye.
It's how you move your head.